Okay, Physics 11. This is our next lesson on mechanical force / mechanical energy. Right, so it follows immediately after our lessons on mechanical energy, kinetic energy, and gravitational potential energy. Okay, so what we'll be looking at today is kind of a combination of the two in the term of mechanical energy. Okay, so we'll just get into it. All right, so when we talk about mechanical force, right, we are actually talking there about the sum of the potential energy and the kinetic energy, okay? So when we go to find this mechanical force or mechanical energy, we're actually going to be using the formulas that we've been using over the past few lessons, okay? So we will still be using our kinetic energy formula, our EK is equal to 1/2 mv squared. We'll be using our potential energy formula, using our MGH, right? We'll be potentially using our work formula, right? Work is equal to force parallel multiplied by delta D, right? Change in displacement, okay? So just kind of be aware of that as we go through. Okay, so we can kind of classify two different types of forces here. One is a conservative force, okay, and this is a force that does work on an object so that the amount of work done is independent of the path taken. So basically, you know, like work being done that it, you know, if you did it in a zigzag motion versus in a straight motion, right? So it's like you start and end on the same place, but it doesn't really matter which way you do it because you start in the same spot and you end up in the same spot, versus a non-conservative force that is work done that depends on the path that's taken. All right, so friction, for example, is a non-conservative force because in that last example I just mentioned about, you know, pushing something along a straight line versus pushing something in a zigzag pattern, well, that force of friction will obviously be more, right? You'll encounter more friction if you try and keep changing directions and doing it back and forth, right? Versus if you just did it in a straight line, okay? Again, gravity would be the good example of a conservative force, right? So again, like if you're lifting a book, it doesn't matter if you lift it in a zigzag pattern or you just lift it straight up, right? Air resistance is so minimal that you still just get the same amount of energy, right? Versus, again, with that talking about friction being a non-conservative force, right? Because it's going to obviously create more work to push something across a room in that zigzag motion versus just in a straight line. Okay, so that's kind of the difference between them. All right, so when we talk about total mechanical energy, okay, as already previously mentioned, it's the sum of an object's kinetic energy and potential energy. All right, so in our lesson on gravitational potential energy, we really just kind of talked about the fact that, you know, when an object is just at a particular height, it has potential energy, right, but it's not moving. And in our lesson on kinetic energy, we talked about, you know, the energy that an object has while it's in motion, right? But if we're talking about an object that's potentially, you know, that's falling, before it's dropped, it only has potential energy. While it's moving, it actually has, like while it's falling down, it actually has a combination of both potential and gravitational energy, or potential and kinetic energy. Okay, so there's a combination there, and we deal with kind of this idea of conservation of energy here, where the amount of energy that you have at the beginning of a scenario is the same as the amount of energy at any other point in the scenario. All right, so in that, you know, using that kind of conservation of energy aspect, right, energy is not created or lost, it's just changed into a different kind of energy, right? You can kind of use, you know, our totals and our equations here to be able to solve for different aspects of the problem, right? Whether it's mass or the velocity or the height that something was falling from. Okay, mechanical energy is also measured in joules, just like kinetic and potential, right? Since you're going to have, you know, this measured in joules plus this measured in joules. I'm noticing a typo here where this says EP and this says EG. Both notations are actually correct. It just depends on the textbook that you're using. I don't know why I switched between them here. I'll edit that before I post the notes, and I'll have them as EG because that's what we've been using. Okay, so again, like I said, with mechanical energy, right, using that kind of law of conservation of energy, your mechanical energy prior to an event, right, is the same at any other point during the event, okay? So because of that, if this is kind of a first point and then this is a second point, right, the sum of the gravitational potential energy and the kinetic energy is going to equal the sum of those two things on the other side. All right, so you might be at different heights, but if you're at different heights, you likely have different speeds. Okay, and then you can again just use the equations we've used for those, right? MGH, and then this is at the first height, and then this is the second height here, right? For EGH2, your kinetic energy formula, your 1/2 MVI squared, and your 1/2 MV2 squared, right? So again, what will likely change is that your heights will change, and therefore your velocities will change throughout a scenario, right? In order for them to still equal the same total, okay? Now, I'm going to focus this lesson on using those these three formulas or four here, right? Using our work is force, parallel times distance or displacement, the kinetic energy formula, gravitational potential formula, and now your mechanical energy formula. Now, keep in mind though, formulas that we used with kinematics, right, our speed being distance over time, and our Vf squared equals Vi squared plus 2AD, or even our D is equal to VIT plus 1/2 AT squared, those can also be used to solve some problems involving energy, right? So like for instance, you could potentially use this equation to find your distance or your displacement that can then be used to find your work, right? Or you could use this formula here to figure out your velocity, which could be used to find your kinetic energy, right? There's a combination of different ways you could do this. So I'll be showing you one way on the board, and then sometimes I'll have a different way put in the notes just so you can kind of see two different options here, okay? So here we go. Let's go in through some of our practice problems. So in this first one, an object is released from a height of 13.5 meters. What is the object's velocity at a height of 9.25 meters? Now you might look at this question and say, hey, that's really similar to when we did our lesson on free-falling objects. And you're right, you could solve this problem using our information on free-falling objects, knowing that gravity was equal to 9.81 meters per second squared, and you had the height, and you knew the change in displacement went from 3.5 down to 3.25, and that acceleration was due to gravity, and your initial velocity would have been 0 because you were not moving at the beginning, right? And you could work itself out that way, or what we could do is use our information about gravitational potential energy and mechanical energy in a combination with kinetic energy and figure it out that way instead. So I'm going to look at it that way, seeing as that's new. So if we're thinking about an object that's being dropped from a particular height, right, the height of 13.5 meters. At 13.5 meters, right, at that height, and it's not moving, all we have is gravitational potential energy, right? It's all EG there, okay? At the height of 9.25 meters, we have a combination of EG and EK, right? Because at that point, it wasn't moving, it was being dropped. By the time it gets to that height of 9.25, it still does have gravitational potential energy because it's still above, right? It's still in the air, but it's also in motion, so it also has kinetic energy, right? So if we kind of think about that idea of, conservation, right? The mechanical energy before the event occurred, right, which would have been our EG1 plus EK1, right, is equal to the mechanical energy after the event has occurred, or at a second point, which is here, which is again our EG2 plus EK2, right? Now, as I mentioned, at that height of 13.5 meters, there is no kinetic energy, right? The velocity would have been 0. This whole thing would be gone, right? And this is our MGH, and then this would equal MGH2 plus 1/2 MV2 squared. And we're interested in the velocity, right? So this is what we're essentially trying to find, is what is that velocity at that particular height, okay? So we can start filling in values, but you quickly realize that we don't have a mass, right? There was no mass of the object ever given to us, right? We had the heights, and we know that gravitation would be the 9.81, but what do we do with this mass? Well, clever little bit of math here. You can kind of factor out that m, right? Leave it alone for right now. You know that that's 9.81 meters per second squared. You know that first height is 13.5 meters, right? Fill in what you do know, and that mass and then 9.81 meters per second squared. That second height is 9.25 meters, right, plus 1/2 times, again, a mass that we don't know, times a velocity that we also don't know, right? We can multiply here and multiply here, right, and what we get is that mass is being multiplied by 132.435 meters squared over second squared, which is equal to, now this is where we're going to do a little bit of algebra here. The mass is a common term to both, right? So it can be factored out. So we can be mass, and then we can multiply the 9.81 by the 9.25, which is the 90.7425 meters squared over second squared, plus 1/2 v squared, right? So I've just factored the m out because the mass wouldn't have changed, and then if you did the distributive property, you'd get that m times that 90, and then plus the m times 1/2 v squared. Okay, so because of that, notice how both sides of the equation here have an m. So I could divide both sides by m, and the m's go away. So now what I've got is this value of 132.435 meters squared over second squared is equal to this 90.7425 meters squared over second squared plus 1/2 v squared. These are the same terms, so I can subtract the 90 from both sides, right? So it'd be 132 minus 90.7, and I get a value of 41.6925 meters squared over second squared, and I'm just left with this term of the 1/2 v squared. At which point I can divide both sides by 1/2, right? That's just a constant, right? Which would be the same as multiplying both sides by 2, which gives me a value of 83.385 meters squared over second squared is equal to v squared. And then all I need to do is square root both sides to get v by itself, okay? So I square root the 83.385, I get 9.13, and notice even with my unit analysis here, when I square root meters squared over second squared, right, it would just turn into meters per second, which is what we want, right? We want a velocity in meters per second. And I needed 3 sig figs anyway, so I'm good there at 9.13 meters per second, okay? So that's how you can use that idea of mechanical energy, right, being the sum of gravitational potential energy and kinetic energy, right, to, they're equal at 2 different points, right, because, yes, there's going to be things like energy loss due to, heat and friction, but when we're talking about things on a larger scale, right, it's relatively minimal in comparison, so this is kind of your ideal scenario of what would work out, okay? Like I said, you could also solve this using your knowledge on freely falling objects, right, where your VI is 0, your mass is irrelevant, your acceleration due to gravity is your 9.81 meters per second squared, right, and you know the distance that it's fallen, right, from the 13.5 to the 9.25, and then you could use that to solve for your velocity in that sense as well, okay? It's just different ways to look at it. All right, in this one, yeah, so again, you see that same thing solved the same there. All right. All right, so let's take a look at practice problem number 2 here. So in this one, a crane lifts a car with a mass of 1.50 times 10 cubed kilograms at a constant velocity to a height of 14.0 meters from the ground. It turns and drops the car, which then falls freely back to the ground. Neglecting air friction, find the following things. So find A, the work done by the crane in lifting the car. Find B, the gravitational potential energy of the car at its highest point in relation to the ground. And C, find the velocity of the car just before it strikes the ground, right? So like the instantaneous second right before it hits the ground after falling freely for 14 meters, right, from its maximum height. All right, so we'll start with A, obviously. The first thing, again, we do is we're going to start listing the things that we know. All right. So in this particular question, things that we knew were the mass, the object, 1.50 times 10 cubed kilograms. We knew that it was a velocity, was a constant. We don't know what it is, but we knew it was a constant velocity. We knew it was being lifted to a height of 14 meters. And what's interesting is that with the fact that velocity is constant, it can kind of lead us to that conclusion that our acceleration would have had to be 0, right? Because if we're not speeding up or slowing down, right, our acceleration is 0 because our velocity is constant. So the first thing that we're being asked to find is work. All right, what's the work done by the crane? Now remember, work was equal to force perpendicular multiplied by our displacement. So if we think about this scenario, right, using like a free body diagram, our object is being lifted up, right? There has been a force applied, right, that lifts the object up, but as it's being lifted up, there's also gravity that's pulling it back down, right? So you have a force of gravity here that's acting on the object, okay? Now, our force perpendicular, we're interested in the force applied here. So don't forget that all of our work with Newton's laws said that F net is equal to mass times acceleration. Now, because it's constant velocity, we know that the acceleration is 0, so we know that F net has to equal 0 newtons. So the two forces that are acting on this particular object are force of gravity and force applied, and if the net force is 0, that must mean that these two forces are equal. Right, so we now know that our force applied is just going to have to equal force of gravity, right? Because it was basically saying that Fa plus Fg would equal 0, and we knew that Fg would be negative, right, because it's acting down, and Fa would be positive, so we can just kind of rearrange that and say, well, our force applied is going to be equal to whatever that force of gravity would have been, right, the positive version of it. And we can find force of gravity by just taking mass times acceleration due to gravity. We have the mass of our object, 1.50 times 10 cubed kilograms, multiplied by our 9.81 meters per second squared, right? And when we do that math, we get a value of 14,715 newtons. Okay, I'm not going to round my answer yet because I do have more work to do, but I will round to my necessary three sig figs once I get to the end. So now I've got my force applied, which can now be used in my work formula. Right, so that's that 14,715 newtons multiplied by its displacement. So it was raised from the ground to a height of 14 meters, so its distance moved was 14 meters. And then I can just do that multiplication and get a value of 20,610. And that would be Newton times meters, right? So Newton meters. But remember that Newton meters and work done is measured in joules, right? So I can put that into my three sig figs. So I'll just use scientific notation here and use 2.06 times 10 to the power of 1, 2, 3, 4, 5 joules. There is the work done by the object. Okay? There's the work done by the crane to move that object that much. Okay? So I'm just going to leave that here as my answer to A, and then we need my space. Okay, and now we'll move on to part B. And part B was asking about what was the gravitational potential energy of the crane at its highest point. Okay, and that one's actually fairly straightforward, right? So using our formula for gravitational potential energy, Eg is mg delta h, right? We have the mass of the object, 1.50 times 10 cubed kilograms. We know that gravitation is 9.81 meters per second squared, and we know the change in height was from 0 to 14 meters. Right? And when we multiply all that together, we actually get the same value of 2.06 times 10 to the power of 5 joules. So you note that, hey, that's the exact same answer we got for work done. It makes sense if you think about it, right? At the beginning, right, there was no gravitational potential energy of this object. It was on the ground. All of a sudden, once it's lifted up, it now has a gravitational potential energy of 2.06 times 10 to the 5 joules. How did it get that? Well, work had to be done on the object to give it that amount of energy, right? So the work done on the object is equal to now what the energy, the potential energy that it has, right? That work was transferred and it gave that object that potential energy. Okay, so now those values are the same. All right, finally at part C, it's asking us to find out what is the velocity just before it hits the ground. All right, so if we think about it, this object was at a height of 14 meters, where all of its energy, right, all of its mechanical energy was solely in its gravitational potential. It wasn't moving, it was just standing. It was just being there, okay? Once it's dropped, it starts moving, it's in motion. While it's still moving throughout the air to the ground, it has a combination of gravitational potential energy. As long as it's off the ground, it does have EG, but it also has EK because it's moving. Now, we're being interested in what's its velocity the instant before it hits the ground, right? So we're thinking just as it hits the ground, what's its velocity, which would mean that up here, you had all gravitational potential. All throughout here, you've got a combination of gravitational potential energy and kinetic energy, and just as you hit the ground, we can assume that your gravitational potential energy, right, the distance between the ground was negligible, it's essentially zero, and everything is now EK. All right, so what that means is we can say that at the beginning, right, EG1 is equal to EK2, right? At the beginning, at the top, the first event of the object raised to its highest point of 14 meters, it had all gravitational potential energy and no kinetic energy, so disregard the kinetic energy aspect of EK1. Just before it hits the ground, it has no gravitational potential energy, so EG2 is nothing, and it's all kinetic. But due to conservation of energy, right, there was no loss, so all the energy that it had at the beginning is now all that it has at the end as well, right? So we have a value for this. We've already calculated it. It's that, I'm going to go back and put in the non-rounded answer there. It was that 20,610 joules. And our formula for EK is 1/2 mv squared. We're interested in the velocity, and we have the mass, right? So we've got this 20,610 joules is equal to 1/2 times our mass of 1.50 times 10 to the 3 kilograms, and then multiplied by velocity squared. So all I need to do here is take my 20,600, divide it by 1/2, divide it by the 1.50 times 10 cubed, and what I get is a value of 274.68, and the units there would be meters squared over seconds squared, right? Because a joule is a Newton meter, and a Newton is kilogram times meters per second squared. So dividing it by a kilogram will get rid of the kilograms, and you're just left with the meter part from the Newton meter, and then meters per second squared. So you get meters squared over seconds squared equals velocity squared, square root both sides, and you get a value of 16.6 meters per second is your velocity, and obviously that's in a downward direction, right? Because it's been pulled down. Okay, so that would be your velocity of that object. So there you go. We found all of the things we needed to. Right, so again, you're seeing the same things here in the notes, right? So calculating F of G, right? And then that value is the force applied, right? And then getting your work done, seeing that it's the same value for the gravitational potential energy, and then seeing that same idea there. This one is a slight different thing that I did. They just kind of said, well, the work done is equal to the change in the kinetic energies, right? And we talked about that before when we looked at the work kinetic energy theorem, right? Because we also had work done calculated in part A, which you also could have applied here, where work was equal to EK2 minus EK1, right? Used that theorem to make it work, and you knew what that same value was, right, of that 206,010 joules, and your kinetic energy at 1 was 0, right? So it's the same, and all these equations kind of interact with each other, and there's not necessarily a preferred way or a right way to do it as long as you're using the right concepts. okay? So your total kinetic energy there while falling is the 2.06 times 10 to the power of 5, and then that allows you to solve for your velocity there of 16.6 meters per second, right? I kind of didn't bother finding the kinetic energy while falling, but all good, right? Well, it's the same. Okay, so moving through. All right, so let's look at number 3. So a nice little roller coaster problem. Okay, so again, in a roller coaster, right, you're experiencing a lot of highs and lows, right? Changes in height and changes in speed, right? But again, we can assume that the mechanical energy is going to stay the same, right, due to conservation of energy. And if you're at a higher height, you probably have a lower speed, and if you're lower height, you have a higher speed. And again, that just makes sense if you've ever been on a roller coaster, right? You're at the top, you're pretty slow, and then all of a sudden you come flying down, and by the time you're down here, you're moving pretty fast, but you're not at the same height anymore, right? And as you kind of move back up again, you can feel it slowing down, right? So if we look at this, what we've got in this concept is that we've got a 846 kilogram roller coaster, has a velocity of 4.15 meters per second at this particular point, okay? Determine its gravitational potential energy, velocity, and kinetic energy at these 2 other points, all right? So we know that here we've got a velocity, so it's not stationary at that point. It is still moving at 4.15 meters per second, okay? And we know its mass, and we know that its height is 30 meters. We want to know, okay, well, what's the combination of the potential energy and the kinetic energy and the velocities at these 2 points here, okay? So once again, that idea is that the mechanical energy is going to stay the same, right? It's going to remain constant using conservation of energy at each of these 3 points, right? So there's a combination of gravitational potential energy and kinetic energy here at A, as well as a combination here at B and a combination here at C, but they should all equal the same total mechanical energy, okay? So we're going to assume 3 sig figs for all our values, even though these are only just showing, 1 in some of these cases, okay? So that's being specified to us. So let's get into this question. All right, so a couple things I'm going to list. Obviously, we have our mass at 846 kilograms. We have 3 different heights. Right, we have the height at A, which is 30 meters. We have the height at point B, which is 10 meters. We have the height at point C, which is 25 meters. Okay, that's everything that we've been given. And like I mentioned, if we're going to think of this in terms of the mechanical energy aspect of it, right, that's going to be the same everywhere. So our total mechanical energy, we can calculate from, we knew the velocity at A, 2. It's 4.15 meters per second, right? So it's going to equal EG plus EK. And right now, I only have enough information to find that total using point A, because it's the only where I also have the velocity. So our total mechanical energy is a sum of the gravitational potential energy at A as well as the kinetic energy at A. Right, so you're using your formula here, your mgh plus your 1/2 mv squared, and we have all of these values, right? We have that the mass is 846 kilograms. I'm just going to leave off my units because I'm not going to have enough space. Multiplied by our gravity, 9.81 meters per second squared, multiplied by our height, which is 30 meters, plus our 1/2 times our mass of 846 kilograms, multiplied by our velocity of 4.15 meters per second squared, okay? And all we need to do there is just calculate, right? So in this first bit, the MGH, right, the 846 times 9.81 times 30, that will give you a value of 248,977.8 joules. The kinetic energy, when you take your 1/2, you multiply by 846, and you multiply it by 4.15 squared, you get a value of 7,285.12 joules, okay? And then you can just add those together, and what you get here is 56,262.9 joules. And if we use our 3 sig figs, it would just be 2.56 times 10 to the power of 5 joules. Okay, so there's our total mechanical energy at point A. So at point B, right, the sum of the gravitational potential and the kinetic energy would need to equal this same value. Okay, and at point C, the same thing. Now, because we're given the heights of both points B and C, we're going to be able to find that gravitational potential energy no problem, and I'll just have to be able to subtract it from the total to get what the kinetic energy would be. And then once we have the kinetic energy, we can just divide it by the 1/2, divide it by the mass, and we'll square root it when we'll get their velocities. Okay, so at that point, I'm going to list ET here as a value that we now know. Right, and we'll move on to looking at what's happening at point B and what's happening at point C. Okay, so as I said, our total would equal the sum of the gravitational potential energy and the kinetic energy at that point. Okay, we know this value is 2.56 times 10 to the 5 joules. This can be found using our mass of 846 multiplied by gravity, 9.81, multiplied by its height, which in this case is just 10 meters, and then that's plus EKB, right? So we're being asked what is EKB there. Okay, so what we can do there is then look at this value here, right? Multiply that through, so you get your 2.56 times 10 to the power 5 joules is equal to, we can do our 846 multiplied by our 9.81 multiplied by 10. That gives us 82,992.6 joules plus EKB, right? So now we have that EGB, we know that value there is 8.30 times 10 to the power of 4 joules, right? Because that was one of the other things asked in the question is what's the gravitational potential energy at point B and the kinetic energy at point B and the velocity at point B, right? I just need to subtract these two to get the kinetic energy, right? And so I'll do 2.56 times 10 to the 5 minus that 82,992.6. I end up getting a value there of 1.73 times 10 to the 5 joules is equal to EKB, right? So that's another value that we were asked to find, right? So there's my gravitational potential at B, there's my kinetic energy at B, and now I'm asked for the velocity. So this value here of the 1.73 times 10 to the 5 joules is equal to the 1/2 mv squared, right? And that's velocity at B. I know my mass is 846, so 1.73 times 10 to the 5 joules is equal to 1/2 times 846 kilograms times my velocity at B squared. I divide both sides by 1/2. I divide both sides by 846, and I get a value of 408.98 meters squared over second squared is equal to BB squared. I square root, and I get an answer of 20.2 meters per second is my velocity at B. Okay, so at point B, the gravitational potential energy is 8.30 times 10 to the 4 joules. The kinetic energy is 1.73 times 10 to the 5 joules, right? Which makes sense that the kinetic energy is more than the gravitational potential, right? It's at a lower height, and it just kind of did a big dip, so it's moving quite quickly, right? Look at the speed difference from 4.15 to 20.2 meters per second, okay? So there we have everything with point B. Now we're going to do essentially the exact same thing, but with point C, right? So I'm even going to try and just save a little bit of time here, where we just change this to point C. So the mechanical total energy is equal to the gravitational potential energy at C plus the kinetic energy at C. that total was still the same, right, that we calculated at the beginning, 2.56 times 10 to the 5. Then what we have is the change in height. This is now 25 instead. So that EG is a value there of, so 846 times 9.81 times 25 gives me a value of 207,481.5 joules, right? Plus EKB. Okay, so now my EG at point C is that 2.07 times 10 to the 5, which again makes sense that this gravitational potential energy at C is more than it was at B, right, because it's at a higher height. Okay, makes sense. So now if we're looking for, well, then what would be the kinetic energy at point C? It's again just a subtraction of that 2.56 times 10 to the 5 minus that 207,481.5 joules, and that actually gives us a value of 4.88 times 10 to the 4 joules, and that's our kinetic energy at C here. Okay, so now there's your gravitational potential energy at C, there's your kinetic energy at C, and then same idea here where your kinetic energy is equal to 1/2 mass times the velocity at C squared, but this value is now 4.88 times 10 to the 4. Okay, the mass is the same. Right, this is now 4.88 times 10 to the 4 joules. You do the same process where you'll take that 4.88 times 10 to the 4, you'll divide it by 1/2, you'll divide it by 846. That will give you a velocity in meters squared, or a value in with units of meters squared over seconds squared, which is 115.322 meters squared over seconds squared is equal to the velocity at C squared. Then you just square root, and you get a value of 10.7 meters per second. Okay, so there you go. Same process for C as it was for B, right? Just change the values as necessary, right? So again, you see there that the speed is less than it was at B. Again, that makes sense based on what the roller coaster was looking like, right? B was near the bottom, right? And then it was moving up again, right? So it picked up gravitational potential energy, right? Because you can see that that value is larger than that value, right? But it lost kinetic energy, and therefore lost its velocity, right? Because the mass was unchanging. So if the mass is unchanging, the only way that that EK can change is by the velocity decreasing, right? So there you go. Now, this was one of those questions that you could have done it using a lot of your kinematics formulas. Okay, so I'm just going to show you that option on this slide here as well. Okay, so you can still get at point B and point C, you can still get your gravitational potential energy the exact same way, right? Your mass times your gravity times your height, right? So you still get those same values that we've already calculated. But you could have found the velocity before finding the kinetic energy. We did the opposite. We found the kinetic energy first and then used the 1/2 mv squared formula to help us find the velocity. But technically the velocity could have also been found, just to kind of give you an alternate way of solving this, using one of our kinematics formulas of Vf squared equals Vi squared plus 2AD. Because you knew the initial velocity from point A, right, being 4.15 meters per second. You knew the acceleration, right, because the object was essentially in free fall, falling down, 9.81 meters per second. And you knew that it fell from a height of 30 meters to a height of 10 meters. So just thinking about things happening in the Y, right, there might have been a different force applying horizontally, right? But that's, you know, not relevant here. We're just thinking about what's happening in the vertical. And in the vertical, the only force pulling it down would have been that force of gravity, 9.81. And your change in distance there was 20 meters, right? So, and you would have gotten the same answer. Okay, so you know, if you if you missed kind of the point about using the mechanical energy as the sum of the gravitational and kinetic, there is kind of a workaround to be able to find the velocity using one of your kinematic formulas, right? And you're getting those same values either way. Okay, so just kind of keep that in mind, that there's always, a couple different ways to be able to solve problems as you work through physics, right? All right, so what you've got now is a worksheet on mechanical energy, and then what you'll see posted later this afternoon as well is your final assessment, right? It's an assignment on everything we've done with work and energy, and I think I've made it like a Google form where you do kind of a combination of multiple choice questions as well as upload your answers to some long answers, okay? And that's your last assessment for your online learning, and then you don't have to hand that in until June 15th. No, not 15th. You have until June 12th to hand stuff in. That's like the last date that I'll be accepting work to be graded for marks to help improve your grade in Physics 11, okay? But, obviously the sooner you get it done, the better. And then you'll get one final video that I'll make for you, but then everything else will just be kind of a work package, like I mentioned, about the waves and efficiency, so you can have a different set of material to kind of look through, as I mentioned before, right? Just to kind of help you feel as prepared as possible for Physics 12 should you choose to take it. All right, and that is it.